Chapter 12, slides 1 through 4. So this chapter starts exploring the functional group called alcohols. And we're going to start with the properties of alcohols and then start talking about how we make alcohols and what we can do chemistry-wise with alcohols. So let's start with the properties of alcohols. If you think about it, an alcohol looks very similar to water, right? The only difference between water and an alcohol is the fact that one side has a carbon attached, while water has two hydrogens on flanking either side. So it probably is no surprise that when you think about the acidity or the pKa of an alcohol in general, that it's very close to water. So let's remind ourselves what the pKa of water is. You guys recall that? 15.7. So alcohols are very close. Now the group, the methyl group, is an electron donating group, and it may be not methyl, it might be ethyl or propyl or some other larger alkyl group, or that alkyl group might have more functionality on it. So this is all going to play a role in what the actual pKa for any given alcohol is. So we're going to see a range for typical alkyl alcohols of about 15 to 18 or 19, somewhere in that vicinity. So you can see that right here. And you can understand that it is close to water because they're very similar. Where does this sit relative to other functional groups? Well, if you recall, an alkane, like, I don't know, butane or propane, has a pKa of any hydrogen on those carbons, given that there's really no polarity, the pKa of those hydrogens is around 45 to 50. Remember, we have ARIO. ARIO is a system that allows us to help qualify, right? Not quantify, but qualitatively assess the acidity of a given compound. So you take off the hydrogen and you look at the conjugate base or the negative charge left behind, and you assess it using the atom, then resonance, then induction, then orbital. An amine, which as we recall is a functional group that is basic in nature. So if it's basic, it's not very acidic, is it? So taking a hydrogen off the nitrogen, right, gets us to a nitrogen minus, but from an atom perspective, it's not super electronegative. So you see the pKa units of 35 to 40 for an amine. That's for a hydrogen on a nitrogen amine. But as we just looked at, a hydrogen on an oxygen, now we're getting somewhere because the atom that you're removing the hydrogen from, bearing a negative charge, oxygen it's pretty good. It's an okay negative charge, right? Because it's on an electronegative atom. So that's why we get into the realm of 15 to 18, much more plausible, much easier to throw a base in there and take off the proton of an alcohol. And lastly, having a halogen with a hydrogen on it, those halogens, Cl minus, Br minus, I minus, those are absolutely comfortable being so electronegative that it can very easily give up the hydrogen. That's why we see such low pKa values, very acidic. Now, does this mean hard and fast we're always going to see between 15 and 18? Well, no, this is just for alkyl systems. But there are instances where you bump up to the next level of looking at charge stability. You can now look at these two molecules I'm showing you down below here, the cyclohexanol and the phenol. Look at the pKa values. What you'll notice is that the cyclohexanol on the left is, a typical alcohol pKa. It's in the 15 to 18 region. Take off the hydrogen, you have an O minus, and it's behaving like an alcohol. However, when you see an alcohol off of a benzene ring, the pKa is said to be 10. That's way more acidic, right? So why is that? Well, if you think about it, we do what we do, right? This goes all the way back to the first chapters of Orgo 1. When you remove the hydrogen off of the OH, you're left with the negative charge left behind, just like you were for cyclohexanol. However, we have more than just the atom. Here we have an obscene amount of resonance around and around the benzene ring. So it's this resonance which greatly stabilizes the negative charge left behind. Thus, if the conjugate base is super stable, then that means it's more willing to give up the proton. That's why we see a much more acidic proton for phenol. Okay, what else about alcohols? Well, given the pKa value, we can also see some variations, not as great as 10, but 12.2 versus a near 16. If you had to assign these pKa values to the two molecules listed below, which would you give? Take a second to think about that. Look at the difference. On the left, you have CCl3. You remove the hydrogen, you're left with a negative charge. On the right, you have CH3, negative charge left behind. So again, we're using ARIO. The atoms, well, they're both oxygen, so that's not telling me anything. Resonance? Nope, no pi bonds. Induction. Now we're getting somewhere. The methyl group is an electron donating group, and the chlorine, the Cl3s, are an electron withdrawing group. If you had an atom with excess negative charge, which would you want? I am circling the more stable one, which means it's much better if you take off the proton. So if you're more willing to let your proton go because what's left behind, the conjugate base, is more stable, then it's a better acid. So I'm going to attribute 12.2 to the trichloro species and 15.9 to the pure alkyl one. Now, all of this is showing you that alcohols are in the realm of acidity, meaning in the lab, you can throw a base in there and deprotonate your alcohol, giving you a negative oxygen. And we've been using these types of systems all along. Since we started learning SN1, SN2, E1, E2, we've been giving you reagents, like NaOET. Well, what's that? That's actually this molecule right here, right? It's an ethoxide, O- with an ethyl group off of it. You can purchase this, right? So alcohols you're able to leverage that acidity and deprotonate alcohols and make them into nucleophiles or bases. So how can we do that? I mean, yeah, sure, we can buy sodium ethoxide and sodium ethoxide, but maybe you purchased an alcohol like the cyclohexanol and you wanted to make that your bulky base and you just couldn't purchase it. Well, you can make it. You just do some acid-base chemistry. So it's important to understand that alcohols are susceptible to bases, strong bases, and we have methods, if that's what our goal is. Oh, I want to take my alcohol and deprotonate it. We have some methods that are much better. Now, do I want to shove NaOH in there? And this is what I'm talking about here. These are like the most common methods if your goal is to deprotonate fully the alcohol. Why do I say that? Well, remember that acid-base chemistry is in equilibrium. So if you want to get all of your alcohol deprotonated, but acid-base chemistry is in an equilibrium, then how do you, manage to use Le Chatelier's principle to get it all the way to deprotonated oxygen? How do I not have it in equilibrium with the starting material? Well, you want to avoid things like sodium hydroxide. What you want to try to do is use things like sodium hydride or sodium metal, like slice a piece of that silver elemental sodium metal. So what does that look like? Well, sodium metal, that's the stuff that you throw in water and it explodes, right? And everyone has a good time. You've got sodium metal. Remember, we've seen sodium metal as a reagent before last semester when we were reducing alkynes. So sodium metal is in its elemental form. It has one valence electron and it wants to give that up. So what it's going to do is it's going to donate it to the oxygen. The oxygen will then release the hydrogen as an H minus. So what do we end up with? Well, we end up with sodium that gave up the electron, so now it's plus. The hydrogen left with its 2 electrons, so it's H minus. Plus the CH3 with the oxygen, which now has a radical. So you actually need to balance this equation. We're not there yet. We actually need 2 equivalents of the sodium for this to work. So now the second equivalent of elemental sodium donates its electron to oxygen. And now we are at CH3 with a full O minus now, right? 3 lone pairs. And the second sodium is the counter ion. Okay? And so now we have our desired deprotonated system. Now, take a look here. I could have just added sodium hydride to begin with, because you can purchase this. And the nice thing about this is that the H minus acts as the base, deprotonating for us. And here's where it gets really cool, is the fact that this is really not in equilibrium. You know why? You form your desired deprotonated methoxide, but H minus with an H plus generates H2 gas. And if that bubbles away out of your solution, you can't go back because it's bubbling. You're actually removing it. This is what's helping drive Le Chatelier's principle in one direction, because you can't put the H2 back on. So if you want to get complete deprotonation, I would use sodium hydride. Sodium metal can be kind of a pain in the butt. It's also hard to measure. Sodium hydride is a powder, and you can actually work with it far easier than sodium metal, because now you've got to slice it, you got to weigh it. It's already getting exposed to the moisture and oxygen in the air. It's kind of annoying to work with. So my choice would be to just use sodium hydride to fully deprotonate your alcohol of choice. Okay, what about properties of alcohols like boiling points and melting points and such? Well, let's think about what aspects of a functional group play a role in making boiling points and melting points high or low. Remember, we first look for intermolecular forces like hydrogen bonding, right? And the alcohol has a hydrogen on a heteroatom. So due to hydrogen bonding interactions, these tend to be high. So when you have an alcohol, they tend to be, for organic compounds, pretty high due to the hydrogen bonding interactions, holding one molecule to another molecule pretty tightly. Solubility in water, well, as long as the number of greasy carbons is low, lower molecular weights, meaning you don't want to have long chains of carbons with an alcohol on it. That one is probably not soluble in water. However, if you keep the carbon chain or the carbon number small, like let's say propanol, it will be water soluble because of the nature of the hydrogen bonding interactions. Like dissolves like. Let me can think about smaller molecules like ethanol and methanol, definitely miscible with water. Okay, last for this set of slides is we're going to talk about naming alcohols. We're just going to add to our IUPAC system. Now, when you have multiple functionality, because we're starting to do that now, you just have to remember that alcohols are pretty high in priority. So in this first case, you'll see that we're going to start numbering from the right-hand side. We're going to find that parent chain. 1, 2, 3, 4, 5, 6, 7. Hept. All right. There's a 2-alcohol, 2-all. And this is probably no surprise because you guys have words out there. You have molecules that you know, like ethanol and methanol, and you can see they end in all. So, you know, surprise ending here. Alcohols end in all. And at 5, we have an ene. And I think that's it. I've covered everything. So now we got to put it all together. 5-6 double bond. It has that trans, orientation to it. So I got to remember to name that. So 5, is that cis or trans? That's trans. So that is going to be E. So 5E. Hept. And you can write 5-ene, 2-all. E is before O. So alphabetically, we put the functionalities in their alphabetical order. How about the next one? Well, let's start numbering around the ring, which is our parent chain at the alcohol. 1, 2, 3, 4, 5. So this is a cyclopent, and it's all alkanes, so penten, and there's an alcohol, and it's at 1, so I don't have to put the 1 in. Feel free if you want to. 1 cyclopentanol, cyclopent 1-all, or just cyclopentanol. If you don't give the number, it's assumed to be at the 1, but any one of those 3 variations is fine by me. Also note that there is a methyl at 4, so there's a 4-methyl I have to take into consideration. And I have 2 stereocenters, so I got to figure those out. Let's see here. At 4, it is, my hydrogen is in the back. It's going to be 1, 2, 3. That is R. With the hydrogen in the back, I believe that is R. And you can take your time and go through it and double check my work. And I also have a 1. Stereocenter. Ooh, okay, so now we've got the oxygen is 1, 2, 3, so it's going in this direction. That looks like it's S, but because the hydrogen's in the front, it too is R. So 1R. All right, now you put it all together, right? You can write 1R, 4R, in parentheses, 4-methyl, cyclopentanol. Phew, that's a lot. All right, well, how about this last one? Well, again, alcohols take precedent over the alkenes and alkynes, and so we're going to start numbering from the right. 1, 2, 3, 4. Don't forget, those are carbons on those linear alkynes. So we have bute, and we've got, let's see, 3-ine, 2-all. Let's put it all together. Bute. Now, This is where I actually am going to put the all at the N, but 3-ine 2-ol. Okay, so there'll be some practice for you guys to try and just see if you get the hang of it.